Now in this lecture we'll listen to questions. On both questions we'll find out the area of a shaded region. So we'll start with the first question. In the drawing we have a big quarter circle. Inside this big quarter circle A or B we have this semicircle and this small quarter circle, and our task is to find out the area of this shaded region. Okay, we know that AO is actually the radius of this big quarter circle equals to 10 units in its length. Again, our task is to find out the area of this shaded region. So first of all, AOB is a quarter circle, and therefore this is a right angle. Likewise, this is also a quarter circle, therefore this angle must be equal to 90 degrees in its size. So in the next step, we define the center of this semicircle. This point is point O. We define the touching point of this big quarter circle with this small semicircle, this small quarter circle. This point is point P. We define this point is point Q. We define this point is point S, and we define the touching point of this semicircle with this small quarter circle. This point is point M. So the radius of this big quarter circle equals to 10, AO equals to 10, BO is also the radius of this big quarter circle, therefore it is also equal to 10 units in its length. BO equals to 10. BO is also the diameter of this semicircle. So the diameter of this semicircle equals to 10, and therefore the radius of this semicircle must be equal to 10 over 2, that is 5. So the radius of B of this semicircle equals to 5 units in its length, and the radius of D is also equal to 5 units in its length. So here, this is point O, we have 2 times point O, so we define the center of this semicircle. This point is point C. Point O is the center of this big quarter circle. So CO is the radius of this semicircle, that equals to 5. And this small quarter circle have an external with this semicircle. That is to say, they touch each other externally, and this point M. And whenever you have an external between 2 circles or quarter circles or semicircles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if 2 circles touch each other externally, then the straight line that connects the circles together passes for their touching point. So in the drawing, we have those 2 circles that touch each other externally. This point P. The center of this circle is 0.0. The center of this circle is 0.M. The side line that connects the circles together is of course the side line OM. And according to this rule 10, the side line OM must pass for point P, that is their touching point. Or OPM is one side line. Again, according to this rule 10, OPM is one side line. So we can implement rule 10 in our drawing. What we call in our drawing, this small quarter circle touch this big semicircle at point M. the center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the center together is of course the straight line CQ. And according to rule 10, the straight line CQ must pass through point M, that is their touching point. So we join point C and Q together by straight line, and according to rule 10, the straight line CQ must pass through point M, that is their touching point. And you can see here that the straight line CQ that connects the circles together indeed passes from point M, that is the touching point. According to rule 10, CMQ is one straight line. If CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. So CQ in total equals to CM. CM is the radius of this semicircle, that equals to 5. Plus MQ. MQ is the radius of this small quarter circle. So we define the radius of this small quarter circle as x, so MQ equals to x. And according to rule 10, CQ in total equals to x plus 5. So it is known CQ equals to x plus 5 units in its length. In the next step, I'll copy right triangle QCO, this right triangle QCO in a new page, and we will implement the Pythagoras theorem on this right triangle QCO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is right triangle CQO that according to the original domain. In this right triangle QCO, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. So that is known. CQ squared, that is the square of the hypotenuse, equals to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared. And it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25. Plus QO squared. QO is the missing side, so we leave it as it is. So it is QO squared. So in total, according to the equation 1, we actually found out that x plus 5 equals to 25 plus QO squared. Here we subtract 25 from this equation, equation 1, and finally get that according to equation 1, QO squared equals to x plus 5 squared minus 25. In the next step, we will join points P and O together by a straight line. is given us a question that the radius of this big quarter circle equals to 10 units in its length. Point C is the center Point C, point O is the center of this big quarter circle. Point P is the point on the quarter circle itself. Therefore, PO is the radius of this quarter circle that is equals to 10 units in its length. PO equals to 10. In the next step, I'll copy the right triangle PQO in a new page and manipulate on it the Pythagoras theorem. PQ is the radius of this small quarter circle that is equals to x according to our definition. Here by PT is a measure for Pythagoras theorem. So actually, this is the right triangle PQO that is going to the original drawing. This right triangle PQO, according to the Pythagoras theorem, PO squared that is the square of the hypotenuse, equals to PQ squared plus QO squared. This will be equation 2. PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing sign, so we leave it as it is. Here we will subtract x squared from this equation 2, and finally get that according to equation 2, QO squared equals to 100 minus x squared. And again, according to equation 2, we actually found out that QO squared equals to 100 minus x squared. This is according to equation 2, and according to equation 1, we have already found out that QO squared equals to x plus 5 squared minus 25. So we have two equations for QO squared. Therefore, we can equation 3 that says that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to x squared x plus 5 squared minus 25, and it is equals to q all squared corresponding to equation 2. Q all squared corresponding to equation 2 equals to equals to 100 minus x squared. So total according to equation 3, I should find out that x plus 5 squared minus 25 equals to 100 minus x squared. Here we will open the brackets of this expression and get that x plus 5 squared equals to x squared plus 5 squared that is 25 plus 2 times x times 5 that is 10x minus 25 equals to 100 minus x squared. In this side of the equation 3 we have 25 minus 25 is 0. So on this side of the equation we left only with x squared here we have x squared plus 25, which is 10x here. X squared plus 10x equals to 100 plus x squared. Again, according to equation 3, if we found out that x squared plus 10x equals to 100 plus x squared. Here we relate x squared to this equation 3, and finally get this according to equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. Here we subtract 100 from this equation 3, and finally get that according to equation 3, 2x squared plus 10x minus 100 equals to 0. Here we divide this equation 3 by 2, and finally we get that according to equation 3, we divide equation 3 by 2 and finally get that according to equation 3, 2x squared over 2 is x squared plus 10x over 2 is 5x, 10x over 2 is 5x, and we have 100 over 2 is minus 50 equals to 0 over 2 is 0. So in total we found out that according to equation 3, x squared plus 5x minus 50 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is of course x. X is the radius of this small quarter circle. The coefficient a equals to 1. The coefficient b equals to 5. And the coefficient c equals to minus 50. So we all need to put the data of our specific quadratic equation inside this formula for x. In this way, we'll find out the value of the values of x, that is actually the radius of this small quarter circle. We do it now and get that x equals to minus b. b is 5, therefore minus b is minus 5, plus minus square root of b squared. b is 5, therefore b squared is 5 squared, that is 25, minus 4 times a times c. a is 1, c is minus 50, so minus 4 times a times c is minus 4 times minus 50, that is plus 200. So minus 4 times a c is plus 200, divided by 2a. a is 1, so 2a is 2 times 1, that is 2. So in total, if you found out that x equals to minus 5 plus minus square root of 25 plus 200. So x equals to minus 5 plus minus 25 plus 200 is 225 divided by 2. So x equals to minus 5 plus minus, the square root of 225 is 15 over 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So according to the first solution for x equals to minus 10. But because of the fact that x is the radius of this small quarter circle, x is a length, and x as a length, it must be a positive number. Therefore, x can never be equal to minus 10, that is a negative number. So we cancel the solution, and we left only with the second solution that is left for x, that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So according to the second solution for x equals to 5 units in its length. Repeat again, x is the radius of this small quarter circle that equals to 5. Our task is to find out the size of this shaded region. Of the area of this shaded region. So what is the area of the shaded region? From the domain, it is very easy to see that the area of this shaded region, in total, it will be equal to the area of the big quarter circle minus the area of this semicircle minus the area of this small quarter circle PSQ. Again, we should find out that the area of this shaded region in total is equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PSQ. What is the area of this big quarter circle AOB? The radius of this big quarter circle AOB is 10, and therefore the area must be equal to pi times pi 10 square over 2. Pi times 10 square over 2. And again, if we found out that the area of this big quarter circle in total it is equal to pi times the radius square over 2. That is to say it is pi times 10 square over 2. Minus the area of the semicircle. Because of the fact that the radius of this quarter circle equals to 5, therefore the area of this the radius of this semicircle equals to 5, therefore the area of this semicircle must be equal to pi 5 square over 2. So the area of the semicircle in total equals to pi times 5 square over 2. Minus the area of this small quarter circle PSQ. Because of the fact that the radius of this small quarter circle equals to 5, therefore the area of this small quarter circle must be equal to pi 5 square over 4. So we have here 10 square is 100, so in total this expression equals to 100 pi. Actually, the area of the quarter circle of course equals to pi times square over 4, because we're talking about a quarter circle. So in total, the value of this expression is equal to 100 pi over 4 minus, here we have 5 square is 25, so it is 25 pi over 2. We multiply both the numerator and the denominator by 2 and get that 25 times 2 is 50 pi. And 2 times 2 is 4. Here we have 25 pi over 4. So here you take 4 as a common factor of those three expressions. And you get that 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So in total, if you found out that the area of this shaded region, in total it is equal to either 25 pi over 4 square units in size, or in terms of numbers it is equal to 19.635 square units in size. And again, if you found out that the area of this shaded region, in total it is equal to either 25 pi over 4 square units in size, or in terms of numbers it is equal to 19.635 square units in size. So we finish with the first question. In the next step, I will present to you the second question, and this was the second question of this lecture. The second question, our task is to find out the area of this shaded region. So in the drawing we have two semicircles that intersect with each other, those 2 points. We know that this is angle ABC that equals to 15 degrees in its side. We know that AB is the diameter of this semicircle, that equals to 5 units. And we also know that those two semicircles can go into each other, that is to say they are identical, and therefore they must have also the same areas. Okay, so again our task is to find out the size of this shaded region. Okay. So, first of all, we know that the diameter AB of this semicircle equals to 5, and therefore the radius must be equal to 5 over 2. So, we define the center of this semicircle. This point is point O. The radius AO of this semicircle equals to 5 over 2. Likewise, the radius OB of this semicircle equals to 5 over 2 units in its length. In the next step, we will define the touching point of the diameter CB with this semicircle. This point is point M. And we will join points A and M together by straight line. By joining points A and M, we created triangle AMB. This is triangle AMB. This is triangle AMB. Triangle AMB subtend on chord AB. Again, triangle AMB subtend on chord AB. That is the diameter of this semicircle. And according to rule 7, any triangle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I'm quickly on rule 7. According to rule 7, if a triangle subtend on the diameter of the circle or semicircle, doesn't matter, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is triangle ACB that subtend on chord AB, that is the diameter of this circle, and therefore according to this rule 7, triangle ACB must be equal to 90 degrees in its size. So according to this rule 7, any triangle that subtend on the diameter of the circle, like this triangle ACB, must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. In our drawing, we have triangle A and B that subtend on AB, that is the diameter of this semicircle, and therefore it must be equal to 90 degrees in its size, according to rule 7. So point O is the center of this semicircle AB. We will join points M and O together by straight line. By joining points M and O together there, straight triangle AOM. This is straight triangle AOM. Straight triangle AOM. This is straight triangle AOM. That subtend on chord MA. Again, straight triangle AOM subtend on chord MA. Likewise, we have triangle ABM subtend on the same chord called AM. And because of the fact that those two angles subtend on the same chord called AM, the size of the same triangle must be twice as large as the size of this triangle that subtend on the same chord called AM. the size of this triangle ABM is 15 degrees, and therefore the size of this triangle AOM must be equal to 15 times 2, that is 30 degrees, according to all 13. All 13. According to rule 13, a center triangle is twice as large as the triangle subtended on the same chord. In the drawing, you have a circle. This is triangle ACB that subtend on chord AB. Likewise, this is center triangle AOB that subtend on the same chord AB. And because of the fact that those triangles, they are both subtend on the same chord AB, the size of this center angle must be twice as large as the size of this triangle ACB. The size of this triangle ACB is theta, therefore the size of this triangle AOB must be equal to 2 theta. So, according to this rule 113, the size of a triangle is always twice as large as the size of the triangle that's subtend on the same chord. Okay. So we can implement rule 13 in our drawing, as I already mentioned before. Those two angles, they are both subtend or called MA. The size of this triangle ABM is 15 degrees, and therefore the size of this central angle AOM that subtend on the same chord called MA must be equal to 15 degrees times 2, that is 30 degrees. In the next step, we will calculate this triangle A and B in two different methods. Then we get an equation that says that the area of triangle A and B according to the first method must be equal to the area of this triangle A and B according to the second method of calculation. The area of this triangle A and B, but before that, here from point M, we will draw perpendicular on AB. Again, from point M, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point P. We define the length of the perpendicular MP as h. So h is the height to the base AB. Again, h is the height to the base AB. Okay. So the area of this triangle A and B, according to the first method of calculation, will be equal to the base AB times the height to the base, that is MP, and MP is h, because it's right 90 degrees with the base AB, over 2. So the area of this triangle A and B equals to the base AB times the height h over 2. And it must be equal to the area of this same triangle A and B if we calculate the area in the second method. In the second method, we take the base as AM. The height to the base is MB. Why the height to the base is MB? Because it's right 90 degrees with the base AM. So it is the height MB over 2. This is equation 1. Equation 1 says that the error of triangle A and B according to the first method of calculation must be equal to the error of the side right triangle A and B according to the second method of calculation. So here we will multiply this equation 1 by 2. And finally get that according to equation 1, AB times H equals to AM times MB. In the next step, I'll copy the right triangle A and B in the new page and analyze this right triangle A and B in order to find out the value of side AM and side MB. This is equation 1. We have AB times H equals to AM times MB. AB is 5. AB is 5. So we substitute AB by 5 and we get that 5H equals to AM times MB. AM and MB are unknown lengths. So I copy the right triangle A and B in the new page and we analyze this right triangle A and B in order to find out what is the length of AM and what is the length of MB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle A and B that are coming from the original drawing. This right triangle A and B, sinus 15 degrees equals to AM over AB. So write it down. This right triangle A and B, sinus 15 degrees equals to AM over AB. So here we multiply this equation by AB. And finally we get that sinus 15 degrees AM equals to AB times sinus 15 degrees. AB is 5, so we substitute AB by 5. And finally we get that AM equals to 5 times sinus 50 degrees. Again, AM equals to 5 times sinus 15 degrees. We will continue to focus on this right line. Again, if you found out that AM equals to 5 times sinus 15 degrees. We continue to focus on this right triangle A and B according to the, we have the, we can say here that cosine 15 degrees equals to MB over AB. And in this right triangle A and B, cosine 15 degrees equals to MB over AB. Here we multiply this equation by AB. AB is 5. So here we get that MB equals to 5 times cosine 15 degrees. So now we have the values of AM and MB. So in total, according to equation 1, 5H equals to AM times MB. Put equation 1 here. According to equation 1, 5H equals to AM times MB. So according to equation 1, five H equals to AM. AM is 5 times sinus 15 degrees times MB. MB is 5 times cosine 15 degrees. So in total we found out that according to equation 1, 5H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we divide this equation 1 by 5. And finally we get that according to equation 1, H equals to here 5 we get cancelled, and we're left only with 5 times sinus 15 degrees times cosine 15 degrees. And again, we found out that according to equation 1, H equals to 5 times sinus 15 degrees times cosine 15 degrees. Actually, we have the trigonometric identity that says that 2 times sinus A cosine A equals to sinus 2A. Here we divide this equation by 2, and finally we get this according to this equation, sinus A times cosine A equals to sinus 2A over 2. So according to this trigonometric identity, we get that equation 1 we have H equals to 5 times sinus 15 degrees times cosine 15 degrees. According to this trigonometric identity equals to sinus 2 times 15 degrees, that is 30 degrees, over 2. Repeat again, according to this trigonometric identity, we get that sinus 15 degrees times cosine 15 degrees equals to sinus 30 degrees over 2. So in total, we should find out that H equals to 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1/2. So in total, H equals to 5 over 2 times 2, that is 4. So H equals to 5 quarters. Here the height MP equals to H is equal to 5 quarters. So according to equation 1, according to equation 1, 5H H equals to H equals to 5 times H equals to 5 quarters. We only found out that edge equals to 5 quarters. So in the next step, we define this shape ABM SA. We define this shape MB, that is very similar to a semicircle. We define the size of this region as B, that is to say it is equal to B as coordinated inside according to our definition. And finally we get the shaded, we define the shaded area, that is the area that we are looking for in this question. It's SC. Because of the fact that those two semicircles are identical, they must have also the same areas. So we can write down that the area of this semicircle AB is equal to the area of this semicircle CB. So according to equation 2, the area of semicircle AB is equal to the area of semicircle CB, because they can run to each other and therefore they are also the same areas. What is the area of this semicircle AB? For the moment, it is very easy to see that semicircle AB consists of those two shapes, and therefore the area of this semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to A plus B. So the area of semicircle AB is equal to A plus B. Repeat again. A is the area of this shape CBA, and B is the area of this shape that looks like a semicircle. And C is the shaded area, that is the area that we are looking for in this question. So in total we should find out that the area of this semicircle AB equals to A plus B, and the area of semicircle AB equals to the area of semicircle CB. What is the area of this semicircle CB? From the moment it is very easy to see that in total the area of semicircle CB consists of those two shapes, and therefore the area of this semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. So, in total, we should know that the area of semicircle CB equals to B plus C. So according to equation 2, we should find out that A plus B equals to B plus C. Here we subtract B from this equation, and finally we get that according to equation 2, A equals to C. So if you know that the shaded area, the size of this shaded area, equals to C squared in size, is equal to the size of this shape, that is actually shape A and B. So in order to find out the size of this shaded region C, we just have to find out the size of this shape A and B, and it will be equal to the shaded area because A equals to C. This region A and B, it consists of two shapes. It consists of sector AOM. This is sector AOM, and it also consists of this triangle MOB. Therefore, the area of this shape AMB must be equal to the area of sector AOM plus the area of this triangle MOB. Okay. So, what is a sector? A sector, the green shape AOB is a sector. A sector is a portion of a circle. It is a portion of this circle. It is enclosed by two radii and RKB between them. Okay. A sector is a portion of a circle enclosed by two radii and RKB between them. The angle between the two radii is theta. The two radii also defined as the legs of the sector. What is the area of this green sector AOB? The area of this green sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, the area of this sector AOB is equals to pi r squared times theta over 360 degrees. So if we found out that the size of this shaded area is equal to the size of this shape ABM, and shape ABM consists of two smaller shapes. It consists of this sector MOA, and it also consists of this triangle MOB. And therefore, in total, the area of this shaded region must be equal to the sum of layers of those two shapes that is consists of. That's that the big shape CBA consists of. So the shaded area in total is equal to the area of this sector AOM plus the area of this triangle MOB. And again, the shaded area in total is equal to the area of sector AOM. The rounded sign above AOM is a sign for a sector. It means sector AOM plus the area of triangle MOB. Repeat again, because of the fact that A equals to C, in order to find out the size of this shaded region that is equals to C, you just have to find out the size of A. A consists of two shapes. The first shape is this sector MOA, and the second shape this is triangle MOB. And therefore, in total, A equals to the size of this sector AOM plus the size of this triangle MOB. So what is the area of this sector AOM? This equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. And again, in total, we found out that the area of the sector AOM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of this triangle OB. There are this triangle MOB equals to the base OB. That's actually the radius of this semicircle, that is 5 over 2. So it is the base OB times the height to the base. The height to the base must create 90 degrees with the base OB. Indeed, MP equals to H creates 90 degrees with the base OB. So it is times the height H over 2. So if you know that there are this triangle MOB equals to the base OB times the height H over 2. As I already mentioned before, the radius of this semicircle is 5 over 2. So r squared is 5 over 2 squared. So it is pi times r squared, that is 5 over 2 squared. And we have 30 degrees over 360 degrees is 1 over 12. Plus OB is the radius of this semicircle, that is 5 halves. And we have times the height H is 5 quarters. And we have to divide it by 2. So we have here pi times 5 over 2 squared. 5 over 2 squared equals to 5 squared, that is 25 over 4. So we have here 25 pi over 4 over 12. Plus, in the note we have 5 times 5, that is 25. 2 times 2 is 4, and 4 times 4 is 16. So today we found out that the shaded area equals to 25 pi over 4 times 12 is 48, plus 25 over 16. 25 pi over 48 plus 25 over 16, in total it is equals to 3.2 square meters in size. So if you found out that the size of this shaded region, in total it is equals to 3.2 square meters in size. So we finished to answer the second question. In the next step, I'll summarize the lecture. I'll start with the first question, of course. In the first question, our task is to find out the size of this shaded region. So in the drawing we have a big quarter circle. AOB is a big quarter circle. Inside this big quarter circle AOB we have those two shapes. This is a semicircle and this is a small quarter circle PQS. Again, our task is to find out the size of this shaded region. So first of all, we define the center of this semicircle. This point is point C. We define the touching point of this big quarter circle with this small quarter circle. This point is point P. We define this point as point Q. We define this point as point S. It is given as a question that the radius of this big quarter circle equals to 10. So AO is the radius, OB is also the radius of this big quarter circle, that is equal to 10. AOB is a quarter circle, and therefore this is a right angle. Likewise, PQS is a quarter circle, and therefore this angle must be equal to 90 degrees in its side. OB is the radius of this big quarter circle is equals to 10, but OB is also the diameter of this semicircle, so the diameter of this semicircle is 10, therefore the radius must be equal to 5. So the radius BC is 5, the semicircle, the radius CD of the semicircle equals to 5 units, the radius CO of this semicircle equals to 5 units in its length. Those two shapes, that is to say, this small quarter circle and this big semicircle, touch each other externally at point M. Therefore, we can implement rule 10. According to rule 10, if two circles touch each other externally, then the side line that connects their centers together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. Point O is the center of this circle, point M is the center of this circle. The side line that connects the centers together is of course the side line OM. According to this rule 10, the side line OM must pass through the touching point, that is point P. Or OPM is one side line. Again, OPM is one side line according to this rule 10. So we can actually implement rule 10 in our drawing. Why can in our drawing? The small quarter circle and the small quarter circle touching this big semicircle externally at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The side line that connects the centers together is of course the side line CQ. And according to rule 10, the side line CQ must pass through point M, that is the touching point. Or CMQ is one side line. Again, CMQ is one side line according to rule 10. We find the radius of this small quarter circle as x. So PQ equals to x, QM also equals to x. And because of the fact that CMQ is one side line, means that CQ in total must be equal to CM plus MQ. So CQ in total equals to CM, that is 5, that is the radius of this semicircle, that is 5, plus MQ. MQ is the radius of this small quarter circle, that is x. So in total, CQ equals to x plus 5 units in itself according to rule 10. So in the next step, I will complete the right triangle COQ in a new page and implemented on it the Pythagoras theorem. This is the right triangle COQ, that the corresponding order of drawing. Only to the Pythagoras theorem, and this right triangle COQ, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. CO is x plus 5, therefore CO squared is x plus 5 squared, and this equals to CO squared. CO is the radius of this semicircle, therefore it is equal to 5. So CO is 5, therefore CO squared is 5 squared, that is 25, plus OQ squared. Here subtract 25 from this equation 1, and find out that according to equation 1, QO squared equals to x plus 5 plus 25. Okay. So according to equation 1, x plus 5 OQ squared equals to x plus 5 squared minus 25. In the next step, we join points O and P together by a straight line. Point O is the center of this big quarter circle, point P is the point of the big quarter circle itself, therefore OP is the radius of this big quarter circle, that is equals to 10 according to what is given as the question. PQ is the radius of this small quarter circle, this is x. And this is a right angle because PQS is a quarter circle. In the next step, I call it the right angle POQ in Olympiad and we implemented on it the Paduras theorem. This is the right angle POQ, this is the comment from the original drawing. This right angle again POQ. PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, this is 100, and this is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing sign, so leave this it is. So in total, we found out that 100 equals to x squared plus QO squared. Here we substituted x squared for this equation, equation 2, and finally found out that according to equation 2, QO squared equals to 100 minus x squared. This is according to equation 2, and according to equation 1, we only found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore we get an equation 3 that says that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to x plus 5 squared minus 25, and it must be equal to QO squared according to equation 2. QO squared according to equation 2 equals to 100 minus x squared. So then according to equation 3, I should find out that x plus 5 squared minus 25 equals to 100 minus x squared. Open the brackets of this expression and find out that x plus 5 squared equals to x squared plus 5 squared plus 2 times x times 10, that is 10x. And we have here minus 25 equals to 100 minus x squared. Here we have 25 minus 25 is 0. After we cancel 25, and after here only with x squared plus 10x equals to 100 minus x squared. Here we added x squared for this equation, equation 3, and found out that according to equation 3, x squared plus x squared is 2x squared plus 10x. Then we substitute 100 for this equation. 2x squared plus 10x equals to 100. Here we substitute 100 for this equation. And so I found out that according to equation 3, 2x squared plus 10x plus 100 equals to 0. Here we divided the equation 3 by 2, and so I found out that 2x squared over 2 is x squared, and 10x over 2 is 5x, minus 100 over 2 is minus 50, equals to 0 over 2 is 0. So those are according to equation 3. We actually found out that x squared plus 5x minus 50 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is x squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And you find out the value of x according to the following formula: x equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared plus 5x plus 50 equals to 0, the coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So we just have to put the data inside of our specific quadratic equation inside this general formula for x, and this way we find out the value of the inverse of x. X is the radius of this small quarter circle. Okay, again, now a specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So x equals to minus b. B is 5, therefore minus b is minus 5, plus minus 4 to b squared. B is 5, therefore b squared is 5 squared, that is 25. Minus 4 times a times c. Minus 4 times a times c is plus 200 divided by 2a. A is 1, so 2a, 2 times 1, that is 2. So we have, inside the root, we have 25 plus 200 is 225. So if we found out that x equals to minus 5 plus minus root of 225 over 2. Here we take root out of this equation, and finally found out that x equals to minus 5, and the square root of 225 is 15. So x equals to minus 5 plus minus 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 5 minus 15 over 2. 5 minus 15, minus 5 minus 15 is minus 5 minus 15 is minus 20 over 2. Minus 20 over 2 is minus 10. x is the radius of this small quarter second, therefore it must be a positive number. X can never be equal to minus 10, so we cancel the solution. And we have to leave the second solution that is left for x, that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So to actually found out that x equals to 5 units in its length. Our task is to find out the size of this shaded region. For the one, it is very easy to say that the size of the shaded region in total is equal to the area of the big quarter circle A or B minus the area of the semicircle minus the area of the small quarter circle PSQ. Again, the size of this shaded region is equal to the area of the big quarter circle, the area of the big quarter circle A or B minus the area of this semicircle minus the area of this small quarter circle PSQ. What is the area of the big quarter circle A or B? The area of the big quarter circle A or B equals to pi times r square over 2. R is 10, so it is 10 square over 4. Because it is a quarter circle, we have to divide it by 4. So in total, the area of the big quarter circle equals to pi times 10 square over 4. Minus the area of the semicircle. The area of the semicircle. The radius of the semicircle is 5, therefore the area must be equal to pi times 5 square over 2. Minus the area of the small quarter circle PSQ. What is the area of the small quarter circle PSQ? We know that the radius of this quarter circle is 5, and therefore the area must be equal to pi 5 square over 4. So we have here 10 square is 100, so in total in the numerator we have 100 pi over 4. 5 square is 25, so in total in the numerator we have 25 pi over 2. Here we multiply both the numerator and the denominator by 2, and finally found out that 25 pi times 2 is 50 pi, and 2 times 2 is 4. Here we have 5 square, that's 25 pi over 4. 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi divided by 4. So in total, we found out that the area of this shaded region, it is equal to 25 pi over 4 square units inside, or in terms of numbers, the area of this shaded region equals to 19.635 square units in size. Okay, thank you very much. So in the next step, we repeat on the solution of the second question. In the second question, our task is to find out the size of this shaded region. So in the drawing we have two semicircles that intersect with each other at those 2 points. Those 2 points, we know that AB equals to 5. So the diameter AB of this semicircle is 5, and therefore the radius must be equal to 5 over 2. The radius of OA is 5 over 2, the radius of OB is also 5 over 2. In the next step, we did the construction, that is to say from point M, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and AB. This point is point P. We define the length of MP is H. In the next step, we join points M and A together by straight line, and we join points M and O together by straight line. So here we have, this is peripheral angle AMB that subtend on AB, the diameter of this semicircle, and according to all 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in size. So peripheral angle AMB subtend on AB, that is the That is the diameter of this semicircle, and therefore it must be equal to 90 degrees in size, therefore need to rule 7. So here we have third triangle AOB, third triangle AOM. This is third triangle AOM that subtend on chord MA. Likewise, we have triangle ABM that also subtend on the same chord called AMA. And because of the fact that those triangles are both subtend on the same chord called MA, the size of the third triangle must be twice as large as the size of this triangle that subtend on the same chord called AM. And because of the fact that the size of this triangle ABM is 15, the size of this triangle AOM that subtend on the same chord called AM must be equal to 15 times 2, that is 30 degrees. So AOM equals to 30 degrees in its size. In the next step, we focus on this right triangle, triangle A and B. We calculated the area of this triangle A and B by two different methods, and then we did the an equation that said that the area of this triangle A and B, according to the first calculation, must be equal to the area of this same triangle A and B according to the second calculation. The area of this triangle A and B according to the first calculation is equals to the base AB times the height PM over 2. We define the height PM as h. So according to the first method of calculation, the area of this triangle A and B is equal to the base AB times the height edge over 2. And the area of this triangle A and B, according to the first calculation, must be equal to the area of this triangle A and B according to the second method of calculation. In the second method, we calculated the area of this triangle A and B according to the following formula, that is equal to the base AM times the height MB over 2. According to the second method of calculation, the area of triangle AB equals to the base AM times the height MB over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled. And after we cancel 2, we left here AB times H equals to AM times MB. AB is 5, therefore we substitute AB by 5, so AB times H is 5H equals to AM times MB. In the next step, I copied the several triangle A and B, and then you further analyze it. This is the triangle A and B, that is going to the original drawing. In this triangle A and B, sinus 50 degrees equals to AM over AB. Here we multiply this equation by AB and find out that AM equals to 5 times sinus 15 degrees. Here, cosine 15 degrees equals to MB over AB. Here again, cosine 15 degrees equals to AM over AB. Here we multiply this equation by AB. AB is 5, so in total we should find out that MB equals to 5 times cosine 15 degrees. This is according to this equation. And we already found out that AM equals to 5 times sinus 15 degrees. Here we have equation 1. According to equation 1, we already found out that 5H equals to AM times MB. Okay, 5H equals to AM times MB. But AM is 5 times sinus 15 degrees. And MB is 5 times cosine 15 degrees. So 5H equals to AM is 5 times sinus 15 degrees times MB is 5 times cosine 15 degrees. Here we divided the equation by 5 and found out that 5H over 5 is H. Here 5 will get cancelled and we have only 5 times sinus 15 degrees times cosine 15 degrees. We have the geometric identity, the trigonometric identity that says that 2 times sinus 8 times cosine A equals to sinus 2A. Here we divided this trigonometric identity by 2 and found out that 2 times sinus 8 times cosine A equals to sinus 30 degrees over 2. So again, sinusoid, again, I should found out that sinusoid times cosine A equals to sinus 2A over 2. According to this geometric identity, we get that sinus 15 degrees times cosine 15 degrees will be equal to 2 times, will be equal to sinus 2 times 15 degrees, that is 30 degrees, divided by 2. Again, according to this trigonometric identity, we get that sinus 15 degrees times cosine 15 degrees equals to sinus 2 times 15 degrees, that is sinus 30 over 2. So h equals to 5 times sinus 30 degrees over 2. So h equals to 5 over 2, and 5 sinus 30 degrees is 1 over 2. So total h equals to 5 over 4 squared in size. And again, h equals to 5 quarters. Because of the fact that it is given as a equation that semicircle AB can go into semicircle CB, they must have also the same areas. That is to say, the area of semicircle AB equals to the area of semicircle CB. We define the size of this shaded area as C, we define this area as B, and we define this area as A. So what is the area of this semicircle AB? It is equals to A plus B. The area of semicircle AB equals to A plus B, and it is equals to the area of semicircle CB. What is the area of this semicircle CB? From the drawing, it is very easy to see that CB in total equals to B plus C. So the area of semicircle CB equals to B plus C. So total, according to equation 2, I should find out that A plus B equals to B plus C. Here, subtracted B from this equation, and I found out that A equals to C. So the shaded area C is equal to the area of this shape A. A in total is equal to the area of this shape. This shape consists of two smaller shapes. It consists of this sector AOM plus this triangle MOB. So because of the fact that A equals to C, it means the size of the shaded area must be equal to the size of this area A. The area A consists of two smaller shapes. It consists of this sector AOM plus this triangle MOB. So therefore, in total, the size of the shaded area is equals to the area of sector AOM plus the area of triangle MOB. The area of sector AOM equals to pi r squared, that is the radius of the circle that contains the sector, times the angle between the legs of the circle that is 30 degrees or 360 degrees. So, what is the area of triangle MOB? The area of this triangle MOB equals to the base OB times the height of the base MP over 2. So it is OB, that is 5 halves, times the height H, that is 5 quarters over 2. So, in total, the area of triangle MOB equals to the base OB times the height H over 2. So here we have R is 5 over 2, so it is R squared is 5 over 2 squared. So it is pi times 5 over 2 squared. And we have here, we have to divide it by 12 because we have 30 degrees over 360 degrees is 1 over 12. Okay. So we have here pi times 5 over 2 squared equals to 5 squared, that is 25, over 2 squared, that is 4, divided by 12. So in total, we have here 5 times 5 is 25, 2 times 2 is 4, and 4 times 4 is 16. And we have here 4 times 12 is 48. So in total, found out actually that the area of the shaded region equals 3.25 pi over 48 square meters inside, plus 25 over 16. In terms of numbers, the size of this shaded area is equal to 3.2 square meters in size. Okay, thank you very much.